Perfect.
Well, it was at the end.
Okay. It is an honor to introduce you to our second speaker, great young mathematician, María Medina. María is now working at Universidad de Granada. Please join and learn with her. Yo desaparezco, María. Te perdí, María, ¿dónde?
I don't know, I think I did something wrong. I don't know what I did.
Okay.
Can you see?
Yes.
But do you see the screen or only me?
No, only you.
Okay. Okay.
Right.
Now?
Perfect.
Okay, thank you. Okay, so let's start. Well, thank you very much. Thank you, Leandro and Joao, for the invitation. And well, I'm very happy to be here because I'm seeing many friends' names, which makes me feel very happy. And I have to say that I was lucky and I didn't have to teach this semester, so I'm not used to use these things. This is my first online talk, so I want to apologize in advance because I'm pretty sure that I will do something wrong, as I already did. So, well, during this talk, I would like to focus, well, I don't know how to move this. I did something wrong again. No, okay. Now. I will focus on studying the very famous Yamabe equation, okay? This equation here, this will be my equation for the whole talk. I will try to find solutions to this equation here. We have minus Laplacian of u, and we have u to the p, where p is the critical Sobolev exponent, okay? And we will consider the equation in the whole Rn. Well, this equation is very famous because of many reasons, in particular because it's very related with geometry, because it's related with the geometrical problem of prescription of curvature on the sphere. But why I'm studying this equation and why I will study what I will study is not because of this geometrical interpretation, but it's because of the interest on this equation, because it is the stationary version, let's say, of the energy critical focusing nonlinear wave equation, this equation here, okay? And why I'm interested in this, because, well, I don't know very much about this wave equation, but people studying this are very interested in some important problems like the soliton resolution conjecture, etc., that consist on classifying characterizing the solutions to this equation. And to do so, they need to know everything that happens with the stationary solutions. So they are always saying that they need to know a complete classification of solutions, of stationary solutions to this. And we are very far from having this classification. So what we wanted to do was to go, let's say, a step farther on the knowledge of the structure of these solutions. Indeed, if we consider positive solutions of the Yamabe equation, they are all completely characterized. We know that they are radially symmetric, and indeed, they are all given by this equation here that I call U, and that I will call the bubble during the talk, okay? This equation here, this function here, which is bounded and decays at infinity as a power minus n minus 2. And well, we know that every positive solution to the Yamabe equation is given by this function here or a translation or a dilation of this function, okay? This is what it's written here, and just remember that every time that I write u, mu, psi, I mean psi is the point where the bubble will be centered at this, and this mu will be the dilation or the concentration parameter. Every time that I write this, I mean this bubble at this point with this concentration parameter. Okay, so for positive solutions, we know everything, but for sign-changing solutions, we don't know barely anything. Indeed, Ding proved existence of non-radial sign-changing solutions by using variational methods in the 86, but he didn't give any information, let's say, about the shape of the solution. But then in 2 different papers, Del Pino, Musso, Packard, and Pistoia found explicit constructions of non-radial sign-changing solutions to this equation. So the first thing that I will do will be to try to understand how are the solutions that they build here. And how do they do it? Well, they say, okay, we know that the bubble behaves good with this equation, so what we will do will be to glue positive and negative copies of the bubble. How? Well, if we see here, this will be our solution, so we will have a positive bubble, U at the origin, and then we will have K copies, K negative copies of the bubbles. Where? Well, centered at these points, psi j, that I call here, which are given by this expression here, and they are nothing but taking a polygon in the 1-2 plane and placing a negative bubble at every vertex of the polygon. Okay, so this will be the solution at main order. This positive bubble, the negative bubbles, and then this function phi that will be small compared to these other functions. To see better in a picture, this is the 1-2 plane. We have the positive bubble and the K copies of negative bubbles here. Well, as you can imagine, this solution is invariant under rotation in the 1-2 plane with this angle here is the same if we rotate this, and it's also invariant under Kelvin transform. Well, if we make K go to infinity, we can think of this function here as a circle, let's say on the equatorial. So we will call this solution a desingularization of the equatorial. It will be like having a Dirac delta along the equatorial. This is why we call this desingularization. Okay, and they prove that this is a solution by using a Lyapunov-Smith reduction method. We will talk about this later. Okay, another interesting property of solutions is what it's called non-degeneracy. What do I mean? Well, if we look at the Yamabe equation, this equation here, and we consider any solution Q, one can check that this equation is invariant under translations, dilations, orthogonal transformations, and Kelvin transform. That is, if Q is a solution, this is also a solution, this is also this and this. Okay, these are the invariances of the equation. Okay, if we keep this in mind, we can define this space here that it's very ugly, but we don't care. Okay, this is a space that I will call tilde I. And the only thing that we have to keep in mind is that these functions that we have here come precisely from the invariances, okay? For example, this function here is related to the invariance under translation, this one here to the invariance under dilation, this is the Kelvin transform, and this is the orthogonal transformation. Okay, this is a space generated by these functions that come from the invariances of the equation. And if we count on these elements, this space can have at maximum this dimension here, okay? This number n will be the maximum dimension of this space. Why do I say this? Well, because if my solution Q, this is a solution of the Yamabe equation, has symmetries, then probably we won't have all these elements here. They will be repeated, so we will have some of them, but not all of them. But this is the maximum number that we can have. And well, if we define also the associated linear operator, the linearized operator around the solution Q that I call LQ, we can define its kernel like this, like the function where this is 0. And one can prove, it's proved in this paper here, okay, in this work of Duicaert, Koenig, Merle, that my ugly space, the tilde I, is contained in this space here. And well, the computations are not completely obvious, at least in some cases, but this is very reasonable to see. For example, if one takes the invariance under translations, one takes this function here, so we know that it satisfies this equation, and we can differentiate with respect to the parameter and then evaluate at 0, and one see that this function here is precisely what we get, and it belongs to the kernel of the linearized operator. And this is more or less the idea with every term here, okay? This all come from differentiating somehow the invariances, so they all belong to the kernel of the linearized operator. And well, in this paper, which is very interesting, it's where they motivate why we should study this type of things. And they also give a definition of non-degeneracy. They say that a solution Q is non-degenerate if this is not an inclusion, it's an identity, okay? If this is precisely the same space as the tilde I that I defined before. So a natural question here is whether the previous solutions that we saw are non-degenerate. And the answer is, in the case of positive solutions, the answer is yes. And in this case, as I said, the solution is radial, it has a lot of symmetries, and our tilde I space is given only by these terms here. The one coming from the dilation invariance and the ones coming from the translation invariance. But the others do not appear, precisely because of this radial symmetry. Indeed, this has a dimension n+1. In the case of the solutions constructed by Del Pino, Musso, Packard, and Pistoia, the answer is also yes. Musso and Wei proved in this paper that these solutions are also non-degenerate, and the dimension of the associated space in this case is 3n. So let me just recall that in both cases, n+1 and 3n, both are strictly less than the maximum number that we defined before, that we said it was the largest possible dimension of my space. So, as it was written in the title of my talk, we can already say what will be a maximal solution. We will say that a solution is maximal if it's non-degenerate and the dimension of this space is precisely this n here. That is, if the kernel of the linearized operator is as large as possible. So the corresponding question is whether there exists a maximal non-degenerate solution, because the solutions that we know are not maximal. So from now on, the goal of this talk will be to try to convince you that the answer of this is yes. So let's start with the case of even dimension. We will see why I say this. We assume that n is bigger or equal than 4, and what we will do will be to try to find a solution which is maximal, and the idea that we have is to try to replicate the construction of Del Pino, Musso, Packard, Pistoia, because we know that it works, it's a solution. So we will try to replicate this in a way that it's interesting for us. How? We had this polygon that I said in the 1-2 plane, and we will replicate it in the 3-4 plane. So we will have negative bubbles at the vertices of a polygon in the 1-2 plane, and also negative bubbles at the vertices of a polygon in the 3-4 plane, okay? And the positive bubble at the origin. Positive bubble, negatives, negatives, and plus a function phi that we expect to be small. We can see it in a picture. This is the 1-2 plane, the positive bubble, okay? Negative bubbles, negative bubbles. And well, just to mention here, these numbers can be different, okay? We can have K bubbles here and H bubbles here. And how is, in this case, the space till the I? That is what I'm interested. Well, we can see that this space is given by these functions. That again, I know this is very ugly, but we don't care. If you remember what we saw before, this is the term coming from the translation invariance. This is the dilation invariance. And these were the terms that we had in the case of positive solutions with the radial symmetry. But in this case, we have more. We have also all these terms here. And what it's interesting is just to identify where they're coming from. If you see, for example, this term here is coming from the Kelvin transform invariance, but involving only the 4 first coordinates, okay? When we have 1, 2, 3, and 4 here. And the same happens with the other terms. This comes from the orthogonal transformations in the 1-2 plane, in the 3-4 plane, and then in the other ones when it's 1 with the others, 2 with the others, 3 and 4 with the others. That is, we have changed, let's say, the radiality. If one think of the radial solution, what we did was to break this radiality in the 1-2 plane, setting these bubbles, and then in the 3-4 plane, setting these other bubbles. And we see that doing this introduces these new functions here. And why is this interesting? Well, these functions are exactly 5 and minus 5, so we have these elements of the in the kernel of the linearized operator. So if we prove that they are all that we have in the kernel, we will have a second example of sign changing non-degenerate solution, which is interesting because we only knew one. So we would have a second one. But even more, if one considers n equal 4, that is dimension 4, we have that these are 15 elements and the maximum number that we were expecting is exactly 15. So this construction here is maximal when the dimension is 4. Well, this is contained in a work with Monica Musso and Yunchen Wei, and the theorem would be this one, okay? For any dimension, the solution that we constructed is non-degenerate, and in the precise case of n equal 4, these solutions are the first example of maximal solution. The idea to prove the existence is it's performing a Lyapunov-Smith reduction method. I won't say anything now. I will talk about it a little bit later. And the idea for the non-degeneracy is to analyze the interaction between bubbles. This is quite technical, very, very technical indeed. And I don't have time to say anything about this part. And well, in analogy with the beginning, when I said that their construction was like a desingularization of the equatorial, this can be seen as the desingularization of the Clifford torus, because in the limit we would have like a Dirac delta on one circle in the 1-2 plane and another circle in the 3-4 plane. Okay, well, why 4 was the good dimension? Well, it was the good dimension precisely because of this speech that I gave, talking about that the elements that we add to the kernel were precisely the ones involving these 2 first coordinates. Okay, somehow we broke the radiality in the first 4 coordinates. So this is, we added the elements related to these first 4 coordinates. This is why n equal 4 is a special dimension to build a maximal solution. But precisely because of this, if we do this also, we set another polygon in the 5-6 plane or in the 7-8 plane, etc., we claim, we don't prove this, but we conjecture that one can construct a maximal solution every time that we have an even dimension. Okay, so this presumably closes the question of the existence of maximal solution in the case of even dimension. But what I think it's more interesting, it's what happens with odd dimensions. Okay, this problem took us very, very long time, but I think that now I can give more or less a convincing answer. In this case, we want to do something similar, but now we need to break this radiality. This is always roughly speaking, but involving an odd number of coordinates, let's say 3. Okay, so we cannot use the previous construction because it worked for even dimension, and we need to figure out something different. And what we did was the following. Okay, we like this idea of a positive bubble at the origin and some polygon, but now what we will do will be to replicate this polygon, but if we think of the sphere in this way, we will have a positive bubble at the origin, and then we will have a circle with negative bubbles at some height from above, and then the same at the same distance from below. So we will have 2 circles here of negative bubbles, which are exactly the same, in such a way that this construction is symmetric in the 3rd coordinate. Okay, this is well, this is just the way of writing this, but it's the same idea, the positive bubble and the negative bubbles. And this construction can be seen as a doubling of the equatorial. Okay, these are like 2 circles which are, when k tends to infinity, which are collapsing to the equatorial, one from above and one from below. Let me just mention here, I didn't say very much, well, I didn't say anything about this before, but for those who are familiar with the reduction method, here, instead of having one parameter as we had before, where we only had the concentration parameter, we have 2 parameters, 2 different parameters here, lambda and tau. Lambda is the concentration parameter of the bubbles here, the same as before, which is of order 1 over k squared. And then we have tau, that is the height here, okay? And this is the order of tau. In the case of n equal 3, this one here. So, well, and we have here L and tau, which are numbers that will be fixed at the end. But just keep in mind that we have 2 parameters to adjust. Okay, well, I just said this. And this construction, which is different from the previous one, is still good because it has some interesting symmetries. It's invariant under Kelvin transform, is symmetric with respect to the 2nd, 3rd, 4th coordinate, etc. And it's also invariant under rotation with the angle of the polygon, the same as before. Just let me recall every time that I say this thing of breaking the radiality, what I mean. If you remember the expression of the bubble when it's centered at this point here and with this concentration parameter, I mean exactly this thing here, okay? And since we chose these points to be 0 from the 4th coordinate and so on, this solution, this function, we can say that it's radial here for the 4th coordinate, etc., etc. But it's not radial when we have the sum of all of these bubbles. It's not radial in the 1st, 2nd, and 3rd coordinate. And this is what I mean when I say that we broke the radiality, because if we just write the expression of the the form of the solution that I want, it's not radial anymore in any of these coordinates, but it's here. So, as you can imagine, the same as before. What happens now to our tilde I space? Okay, now we have built a function which is not radial in the first coordinate, so I expect that these are the new terms appearing here. And this is exactly what happens. We have, as always, the translation invariance term, dilation, and then I have the terms coming precisely from these first three coordinates. And well, these elements here can be seen to be linearly independent and to belong to the kernel of the linearized operator. And again, good news, if n is equal 3, these are 10 elements, which is exactly the largest possible dimension of the space. So if we prove, because we didn't prove it yet, if we prove that this is a solution, that we can find a solution that main order has the form of these two circles, we will have a solution with maximal rank for dimension n equal 3. And if we prove that it's non-degenerate. Okay, so let me just try to convince you very briefly why this is a solution. I will just say some words about the difficulties that we found. Okay, we did it by performing a Lyapunov-Smith reduction. What do I mean? Well, I mean, this is the solution that I want. Okay, this is not a solution, but I expect that this is almost a solution. So I will try to find some u, which is this approximation plus a small function phi. And saying that this is a solution is exactly the same as saying that phi satisfies this equation here, where this is a linear operator, this is an error term, this term here that can be thought as how far is my approximation to be a solution, and then a nonlinear term here. Okay, so what we will try to do will be to try to find phi solving this equation. But even more, we will do it trying to find this phi around every bubble. We will write it in this way. These are the bubbles which are upstairs, these are downstairs, and this is the central bubble. So we can write this equation here as these systems of equation. We don't care about the form, the same. These are the equations for the bubbles which are in the circle above, the circle below, and the central bubble. And well, just an observation, since we want some symmetries in our solution, we need to choose to find this function having certain behavior to assure that my solution has the symmetries that I want. How do we do it? Well, it's more or less always the same scheme for these reduction methods. We will try to use linear theory and then to apply a fixed point argument. So just as a starting point, this would be the linear theorem. In the work of Del Pino, Musso, Packard, and Pistoia, they prove that if we have this problem here, which is the simplest way, the simplest one, this is the linearized operator around the bubble, and this is a function h. They prove that if h is orthogonal to the kernel of this operator, then this has a unique solution. Okay, these functions are precisely this, that if you remember were the functions in the kernel of the linearized operator around the bubble, the case of the positive solutions. So if this is orthogonal, we can find a unique solution of this. And what's more interesting for my talk, we also have an a priori estimate. We can prove that the size of phi is controlled by the size of h. These are some weighted norms that, well, it's not important right now, just to keep in mind that this is controlled by the size of this. Okay, my problem, of course, is not is not linear, but as I said, we want to apply some linear theory and the fixed point argument. We already have the linear theorem, so what we have to do is to see that my nonlinear term, this term here, satisfies, well, is orthogonal to the kernel of the linear operator, so I can apply the linear theory and then a fixed point argument. And well, this was the equation for the central bubble. If you remember, this was psi. And well, precisely using the symmetries of the functions, one can see that this is orthogonal, and so we can apply a fixed point argument to conclude the existence of this function psi, which using the a priori estimate, whose size is controlled by the size of the functions at one of the other bubbles plus this term here, and the same for dimension 3. And this term here is given by the error of the approximation, okay? Here in this term is hidden the error, which is a linear term, it's just a constant. So this will be what imposes the size of this function. But what's more interesting, it's okay, we can solve the central bubble equation, but what happens with the others? Okay, the others, if we see at one of them, here we are not so lucky because we don't have so many symmetries because we are just now like centered upstairs, let's say, so we cannot apply the linear theory to these elements here. This is not orthogonal to the kernel, so we cannot do it. But we can do it over a projected version, let's say. Instead of solving only this problem here, we can solve this other problem here, adding precisely the projection of this term on these elements of the kernel. If this is not orthogonal, what I do is to subtract the projection on the elements of the kernel in such a way that all of this is orthogonal. And I can apply the theorem that we found before. And as I said, these constants here are precisely the projection of H in this element of the kernel and H in this other element of the kernel. So if we want to apply this to our nonlinear theorem, what we will have is the following. Well, this is the same, okay, this is my equation, the projected version, and these constants will be given by the projection of this on this. Well, just to mention here, an important point is that this is a nonlinear term that depends on phi, and I expect phi to be small, so probably this will be a very small term. But this term here does not have phi, this have a fixed size, so this will be the large term here. I expect this to be smaller than this one, and the same here. So, since what we wanted to prove was that this problem with a 0 here has a solution, what we want to do is to choose the parameters L and T that I said before that were two parameters that were going to be fixed later. We can try to find some parameters L and T in such a way that these two constants are 0. And to do so, we need to compute the projection of these terms here, expecting, well, as I said, we expect that this is the main order of the projection, so this will give us how to choose the parameters. And indeed, if one does this, this is precisely what one gets in high dimensions, which is perfect, because this means these are numbers, okay, the n, en, these are numbers, we don't care. This means that we can choose L and T in such a way that at main order these cancel out, which is what I want. I want to make this 0. But, and this is why this case of the odd dimension was very much difficult than the other, this thing does not work when dimension is 3 or 4. What do I mean? This works But here we are using that the projection of the nonlinear term is smaller than the projection of the error term. So at main order, we know how to cancel the parameter. But in the case of dimensions 3 and 4, the projection of the nonlinear term is too large. That is, the projection of the error is smaller than the projection of the nonlinear term. And then we cannot control the main order of this thing here, and we cannot cancel the parameters to have that the projections are 0. So we need to do something different. And what we needed to do was to understand why this is happening. And well, if one pays attention, as I said, since the right-hand side of my problem determines the size of my function, and the error term is the largest one, the size of the error term is the one that gives me the size of phi. Because if I make phi smaller in the fixed point argument, I will reduce the size of the nonlinear part, but not the part of the error. So this is the term that determines the error term that determines the size. But when one computes the projection, what happens here is that the largest part of the error, we can just think of the error as two different parts, the largest part is symmetric. And this means that when we compute the projection, we don't see this term. So the main order term of the error does not appear in the projection. And it appears the second order term, which is smaller. So when we compute also the projection of the nonlinear term, it happens to be greater than this one. It's smaller than this one, okay, but this one we don't see it, and is bigger than this one. So what we thought is, okay, so if this is what's happening, that the error is large, but the large part is symmetric, maybe something similar is happening with the nonlinear part, okay? It will have a large part, but maybe we can make it to be orthogonal to the kernel, so the projection will be 0. And this is what we had to build here. We had to decompose our function phi in two parts, a symmetric part, which is a large but symmetric part, and another one which is not symmetric, but we expect to be smaller. And how did we find these two different parts? Well, we considered the error, we chose the symmetric elements, the large symmetric elements, and then term by term, we found a part on the nonlinear term, which is also symmetric and large, and we solved this equation here with only these parts in such a way that this function is large, but it will be symmetric. And at the end, in the reduction procedure, we won't see it. And then we have another part which is not symmetric. This would be like the original problem, let's say, but it's smaller. And again, the size of this, when we perform the fixed point argument, will be determined by the size of this. And as I said, the non-symmetric part of the error is smaller. So we will be able to ask a smaller size of phi of this part here, that is the one that we will see when we will do the projection. So this is more or less the idea of how we solved this difficulty. This is very, very technical because we have to identify term by term which parts are symmetric, which part is large, small, etc., etc. But at the end, it works. And as we will see, for example, for the non-symmetric part in the nonlinear term, we can see that it depends in a term which is the non-symmetric. This was what we had originally, but now we expect this term to be smaller, so this term will be better than before. And then we also see the bad part, the symmetric part here, but now this term appears smaller, okay, with a smaller factor here. So we can do the fixed point argument maintaining the large size on the symmetric part here, because we don't care, because we have this that makes it smaller. But then here we can refine and we can apply the fixed point argument in a ball of smaller size. And Then proceeding like this, what we get is exactly the equation that we were looking for, okay? Now the main term comes determined by the error, which has this size, and the nonlinear term is something smaller that we can control here. So if we do this, we can find parameters in such a way that this is 0, so phi solves our equation, and therefore our function u is a solution to my equation. That was what I wanted to prove. Okay, so more or less, if I convinced you, this would be a maximal solution in the case of odd dimension. But well, to be honest, this is not true, because when I gave the definition of maximal solution, I said that the solution had to be non-degenerate. And we didn't prove non-degeneracy, okay? We proved step 1, which is finding the solution which has maximal rank, but we didn't prove yet non-degeneracy. This is an open problem, and maybe this will be done someday, but up to this point, let's say that my construction is the natural candidate to be the maximal solution in dimension 3, but we don't know if it is. And just to finish, let me mention that if we can prove non-degeneracy, this presumably closes the existence of a maximal solution in any dimension, because we think that we can combine these constructions to have something maximal in every dimension. For example, in dimension 5, we could have a desingularization of the equatorial in the plane 1, 2, and then in 3, 4, 5 coordinates, this doubling construction. In dimension 6, we can have 3 times the desingularization, or twice the doubling construction, and the same for dimension 7, 8, 9, etc. So if one can do this, which is something that I don't recommend, because just with one construction, this is the computations are a nightmare. But I guess that if one can do it, probably this gives a maximal solution in any dimension. And well, the first part, the case of dimension 4, the even dimension is contained in this work here. And the case of the candidate for the maximal solution in dimension 3 is contained here. And that's all.
Thank you, Maria. Great talk. Okay, any question, comment? I don't know if you have comment in the chat.
I don't know. I did something wrong again.
No, it's okay. Well, we don't have any comment. Okay. Thank you, Maria, again. Well, now we